Hello, my name is Dmitry Ulyanov, and I would like to present the design of the Intelligent Assistive System for a sailing vessel, which I call a Ghost Crew. And the purpose of the design system is to assist a person in charge of the sailing boat in operation of its components like steering, sails, standing and running gear, and standing and running rigging. The system would help to perform some maneuvers which in real life normally would require the cooperation of several members of the crew. But the intelligence system could create a passage plan, assist in navigation and collision regulations. The system is a composition of hardware integrated into the sailing boat and the intelligence software which controls it. So the system decides what assistive actions to take depending on the responsibilities assigned to it. For example, the skipper may want to take the helm, which is a steering wheel, but assign the system to control sails angle and adjust sails area to keep it effective. But the Ghost Crew would take inputs from various sensors of the boat and could make adjustments in the course of the boat. The inputs could be the wind speed and direction, the speed of the boat, current depth, velocity of the tidal stream, magnetic and true course, GPS positions. There are plenty of variables to take care of. And there are three main actors in the system: the captain, the AI skipper, and the AI crew. And these actors generalized by the abstract actor, the sailor. So the role of the actors is to take orders from the user and from the actor, which is higher up in the hierarchy. The user can switch roles. One time he wants to be a captain, the next time he would like to be an AI skipper or AI crew. Then the other actors would become a subsystem of the whole system, and they would take control of the use cases that are assigned to it. There are many use cases in this diagram, and they all connected in some way. They include or extend each other. So I have picked 5 of them to present and designed the DOM model for them, class diagram and the sequence diagram. And so the 5 are display information use case, the view pilotage information, create passage plan, and steer yacht to waypoint, as well as edit orders. Okay, now let's take a look at the class diagram. A closer look. Let's zoom it in. Okay, right here at the top we see our actors presented as classes: captain, AI skipper, AI crew, and they are all generalized in the sailor class. And the sailor class instantiates the orders manager, which implements the orders queue interface. The orders manager can be only one because there should be no copies of the orders. So there should be only one queue of orders shared by all sailors. That's why the orders manager implements the singleton pattern. This is to make sure that all sailors they have exact same copy of the queue. Now the captain, AI skipper, and AI crew, they have an aggregated relationship to a command class, which is an abstract class that implements the sailor's command interface. Classes like display information, create passage plan, steer yacht to waypoint, they are concrete implementations of the command class. and they encapsulate methods of the dependent classes in their execute order method. Now, when the captain class calls the execute order method of the display information concrete command, it triggers the methods of instances of a screen class, of a YAT specs manager, of the passage plan manager. The YAT specs manager implements the YAT specs DAO interface, and this allows the specs manager to call the YAT specs DAO object and return all the properties of this object into the display information class, which will then call the generate view data method and return all this and would return the generated view to the screen class, which will then render the view to the real screen. Now here's another design pattern, observer. It observes the subject, which is updated by the steer YAT to waypoint command. So whenever the subject is updated, it notifies the events manager, and events manager events manager, it binds the observer with the subject first, and then whenever the subject is updated, the observers are notified about this change, and all classes that implement the observer, that extend the observer class, they can update their properties or call methods to update their references and associations. Let's say the steer YAT to waypoint class. It controls the hardware systems of the boat in real time. Like it controls the course, sails, and steering, and the real life information can then be displayed on the screen using the observer method. So whenever the execute order command is executed, the subject gets updated and it notifies all the observers. Right, here is the sequence diagram of the edit orders queue use case. It describes the flow of orders in the queue. Let's take a look at it closer. Let's say the captain the captain class would like to give an order to the AI skipper, and the command is create passage plan. So in its constructor, the captain would instantiate the orders manager queue, which is a singleton. It would register in the queue of the orders manager. It would obtain the ID of the queue where it's supposed to post all the orders and where to read the orders from. The same for the AI skipper. It would register the instance of the orders manager in its constructor. It would obtain the ID of the queue and would listen this queue for any orders relative to him. Then the captain would like to give an order to a skipper. It would instantiate the create passage plan command. It would call the get orders queue ID method of the skipper, which would return the ID of the queue where the orders are supposed to be posted. So as the captain has the ID of the queue, it can now add order to that queue, which it does. The AI skipper runs an execute method in a loop, and in one of the iterations, it gets an order from the orders manager, and it executes the execute order method of the create passage plan concrete command. As it executes it, it updates the status of the order inside the orders queue, inside the orders manager, and then the captain obtains the status of the order, and it removes it, and then the orders manager removes it from the queue. Here's another sequence for the display information use case. When the captain wants to display information, it would call the execute order of the concrete implementation of the command, which is display information class. And the display information class would call the internal function collect information. In return, it would call the method of the passage plan manager, the get plan method, and this method encapsulates methods of the passage plan class to get the course of the ground, the course to steer, the time of arrival, and the waypoints. All these variables are returned into the collect information internal function, and then the display information proceeds to the next function, which is get specs from the yacht specs manager. And the same story is over here. The specs manager encapsulates the methods of the yacht specs. These are the getters of the cruising speed, of the draft of the boat, of the beam width and the length of the boat. All these variables are returned back to the display information collect information method, and based on these variables, the display information would generate the view data. It would then execute the render view method of the screen class. Next to the create passage plan sequence. Sorry for the quality of the picture, it's really hard to read. So when the captain wants to create a passage plan, it would add an order to the orders manager queue. The AI skipper would listen for that queue by constantly running the get order method in a loop, and when it finds a new command in the queue, it would call the execute order method, which is common for all the command classes. The create passage plan would then reset the current passage plan which is stored in the passage plan manager. Then it would take the status of the GPS satellite. It would run the get status method until it returns the success or a ready state. It would then get the latitude and the longitude of the boat. It will take the get wind method of the weather class. It would call the getter for the temperature properties, and collect the specs of the yacht from the specs manager. When all the variables obtained, the create passage plan command can run the compute method, which will create an instance of the passage plan DAO object, and this object now can be saved into the passage manager by running the save plan method. Next, we will set a new order status in the orders manager queue, and when the captain reads statuses of the given orders, it will execute a new order, which is a display information. The display information will take all the specs of the yacht. It would get the passage plan from the passage plan manager. Then it will generate all the view datas, and it will render the view which is a method of the